In this video, we're going to look at Unit 5, Lesson 11 for Algebra 1, Modeling Exponential Behavior. We're given the graph of f of x, which is defined by 400 times 0.2 to the x. Identify an approximate graphing window for what they're showing us. So when you're in a graphing window, you want to identify the x values and the y values. So I'm just going to highlight these x values in this orange color and then the y values in this blue color as I write them out, just so we can keep track. So the x values start at 0. So 0 is less than or equal to x, and then we just want to figure out what they go to. And we can see that there's kind of 5 dashes that each 10 is split into. So that means each one is counting by 2. So we're at 40, 42, 44 is our top there. Then for the y's, again, starting at 0. And then we can see that these y intervals, there's again 5 dashes splitting up 500. So each of them is worth 100. We get to 1,000 and then one more. So 1,100 is the top there. So our graphing window for x's 0 to 44. Y's are 0 to 1,100. Then it wants us to suggest a new window that would make the graph more meaningful or informative and then less meaningful and informative. Because when we look at this, we can see the graph is just really tiny in this corner. There's a ton of grid and not a lot of graph. So it really doesn't do us any good. You can't really approximate anything with this. It's too zoomed out. So if we're going to take a look at making this more meaningful, we would want to be able to see more graph, right? And if you remember, this equation for this was 400 times 0.2 to the x. And so you can just really kind of look at this graph and try and figure out a new window. You could also use some of the information here. So for instance, we know that this is the initial value and we see that it's decreasing. So we don't really need anything that high over 400. So maybe we just cut it at like 450. And so we don't need anything bigger than 400 really. I like to just have a little bit above it so you're not just cutting it right where it starts, but you don't need to go much over 400. And then you can just extend this a little bit. Now, as we get closer in here, you don't necessarily want to do this because there might be some stuff happening down there. So maybe you want to extend this out to like 10. And again, this is not the only answer. This is just kind of what I'm thinking. So for the x's, I would still be good starting at 0. And then now maybe going up to like 450. Because we know it starts at 400 and then drops. And then the y's, that's the y values, not the x values. Okay. So the y values 0 to 450. And then the x values probably 0 to 10. You could maybe stop at 8. And now if you were actually graphing this, then you could see once you get a more informative window, then you can adjust from there. So if you could still see that you needed some more, you could always change again. All right, then if we wanted to make it less informative or meaningful, now exponential functions, like the initial value starts at x equals 0. So adding in negative space, and let me switch this. Let me do it from this side. So adding in negative x values and extending to the left isn't going to matter. It's not going to make it more meaningful because you're not going to need that data because the initial value is 0. So anything backwards isn't going to be helpful because it's before the time started. And then also exponential values don't dip below the x-axis. They level out at the bottom there. That x-axis kind of acts as a border. It's called an asymptote. So adding in negative values below this x-axis, so negative values for the y, also isn't going to be helpful. So if we wanted to make this less, So I left this border the same, right? I left the max, I left the top of the x's and the top of the y's the same, but we would add in some negative values. So maybe negative 10 is less than or equal to x is less than or equal to 44. So that's not going to make it helpful. And if we added in some negative y values, maybe we dropped to negative 200 is less than or equal to the y is less than or equal to 1100. That's certainly not going to make our window any better. Next activity is going to be looking at the heights when we bounce some tennis balls. So you're going to be deciding on what type of model would represent the relationship best. Then you're going to develop an equation and use it to answer some questions and then discuss your strategies. So here are the measurements for the maximum height of the tennis ball after bouncing several times on a concrete surface. So we see the number of bounces and then the height in centimeters. And go ahead and answer the questions in your workbook and then come back for me to discuss and work through them. Number one, which is more appropriate for modeling the maximum height in centimeters of the tennis ball after n bounces? A linear function or an exponential function? And use data to support your answer. So remember, linear function, the average rate of change stays the same, or an exponential function, the average rate of change changes, okay, increases or decreases. So if we just look at the change per time period, we'll be able to see if it's staying the same or if it's changing. So if I do 80 minus 150, I get negative 70. If I do 43 minus 80, I get negative 37. 20 minus 43 gives me negative 23. And 11 minus 20 gives me negative 9. Now, these are pretty significantly different, right? They're not all around the same number. You have a pretty big difference here. So I'm going to say exponential because the average rate of change is decreasing over time, right? We went from a change of 70 down to 37, 23, 9. So that I would say an exponential function. Regulations say that a tennis ball dropped on concrete should rebound to a height of between 53 and 58% of the height from when it was dropped. Okay, does this tennis ball meet this requirement? Explain your reasoning. So to find the percent that it changed, you would take the new bounce divided by the one right before it. So if we look at 80 divided by 150, this is going to tell us our percent in decrease. And so 80 divided by 150 gives us 53 or 0.533, which is really 53.3%. And then if we looked at it from the second bounce, you do the second divided by the first to see that percent in change. So 43 divided by 80, and you're going to get 0.537, which is about 53.7%. And then the next one, 20 divided by 43. So 20 divided by 43 gives us 0.465. So 46.5% there. And then 11 divided by 20 gives us 0.55. So 55% for that one. So then when we're looking at this, we see, this, most of them are, right? So 53%, 54% if you round up, 55%. So those ones are all between the 53 and 58. And then we see, you know, this third bounce is kind of weird because that one's down at 46 or 47%. So that data point tells us maybe there was a measuring error or something, but we see the other ones are within that. And then we note that there's maybe something weird about that third bounce. Write an equation that models the bounce height h after n bounces for this tennis ball. So in writing your exponential model, right? So our exponential equation uses an initial value, and then you have a growth factor to an exponent power, right? So our initial value in this case is 150 centimeters. And then our growth factor is what we just calculated in all of these percents, right? And so we had 0.53, 0.533, 0.537 in those first couple. So I'm just going to use 0.53 in here. You could use 0.5, 0.52, 0.54, something like that. And so this is going to be the height equals 150 times 0.53 to the n power for the number of bounces. About how many bounces will it take before the rebound height of the tennis ball is less than 1? So now you would use your equation to model this. So we can just multiply this number by 0.5. You can either plug 5 in for n into this, or you can keep multiplying by the growth factor of 0.53 from your table, okay? So I'm going to do 11 times 0.53 and get 5.83. Then at 6, so and I would multiply it by 0.53 again and get 3.089. Okay, seventh bounce, so multiply by 0.53 again, and I would get 1.64. Multiply by 0.53 again, and we would get 0.87. So after 8 bounces. Now that's using from this last place here, right? So we could also plug it into here, and it's going to be a little bit different, okay, because these aren't exactly 0.53 going down. But so if I plugged it in here, let's see what we get if we plug 8 in. What would we get? So 0.53 to the 8th power, and then times 150 gives us 0.93. So pretty close, right? Just one is going on from our data using the growth factor we decided, and one is using our equation to model it. So 2 different ways, similar thing, gives us 8 bounces. So how did you decide if the relationship was linear or exponential? And remember, that was looking at the rate of change. Okay, so the average rate of change would be constant for a linear, where the average rate of change is not equal for an exponential. So we, or at least that's the way I decided, maybe you did something else, but that is what made me think exponential. And then the data did support that, right? So as we kind of looked at the rates of change going down of those percents, it was following that pattern besides that third bounce. And when I used the equation to get 8 bounces and the table seemed to match up. Third bounce, maybe calculation error, right? Maybe, whoops, maybe they just wrote down their number wrong, measured wrong, something like that. There's always human error in experiments. And then how long could we expect this behavior to continue? Will it go on indefinitely? And no, it's not going to go on indefinitely, right? At some point, the bounces just makes it roll, okay, or stop. So it either just starts rolling along the ground or it stops, because you're not going to keep bouncing 0.01 centimeters. It just stops at some point. And a reasonable domain. So if you think of how big a centimeter is. 2.5 centimeters is about an inch. And so, I don't know. I guess you could go to 8. I feel like it's going to start rolling in here. That feels like it's not really bouncing anymore. So 0 to 8 should get us the time that it stops. So something around there. Your domain could certainly be a couple smaller or bigger than mine. Activity 11.3 is optional. Your teacher may or may not do it. It does require that you measure some different heights. So if you did this activity in class, you'll need to make sure that you talk to your teacher about it. Otherwise, you can skip it and move over to 11.4, which is looking at another example of a bouncing ball. So you're going to compare this ball to the tennis ball, create an equation to model it, and then discuss it. The table shows some heights of a ball after a certain number of bounces. Is the ball more or less bouncy than the tennis ball in the earlier task? Explain or show your reasoning. So the bounciness is really kind of like the growth factor, right? So more or less bouncy, we would be wanting to look at the growth factor. How much of its initial height does it lose on each bounce? If it loses a lot, then it's not very bouncy. If it doesn't lose very much, then it's pretty bouncy. So we can look here and we can do 51.5 divided by 73.5 to figure out that growth factor. So this one is equal to 0.70, which means it's keeping 70% of its bounce. And then we can do 36 divided by 51.5 and get 0.699. So again, basically 70%. So this one is keeping 70%. So the tennis ball was keeping 53%, where this ball is keeping 70%. So this one is more bouncy. Okay, it's keeping a lot of its initial height. From what height was the ball dropped? Okay, so we just figured out that going this way, we're multiplying by about 0.7. So then let's take a look if we go backwards from this. Okay, so this was multiplying. So if you want to go backwards, you can divide by 0.7 to find those other values. So let's take 73.5 divided by 0.7. And we'll find out that this would have been about 105. And then we can divide by 0.7 again, and we'll get 150. So we could say 150 centimeters is where we think it was dropped from. So then let's write an equation, and remember that the equation, so this one's height equals, and your equation starts with the initial value. So where did we just decide we dropped from? Was 150. Then we take the growth factor. How much of that bounce was it retaining? And that was 0.7. You can put 0.70. You don't really need that 0. And then to the n power. So which graph, A or B, would more appropriately represent the equation for H in this problem? So when we're looking at the number of bounces that a ball makes, we're not going to look at something where n equals 1.5, because that would be 1.5 bounces. So the only thing that really makes sense is whole number bounces. So we would only have values at 0 bounces, 1 bounces, 2 bounces, 3 bounces, and so on, no decimal versions. And then will the nth bounce of this ball ever be lower than the nth bounce of the tennis ball? And this is going to be no, because their initial value was both at 150, right? So they both started at 150. And the tennis ball is less bouncy than this ball. So when they first drop, okay, that second bounce on this one is going to be higher. And then it will always retain 70% of its bounce, where this one, or sorry, where the tennis ball is only retaining 53%. So then the tennis ball will never be higher than the tennis ball after the initial bounce. So how are the data here different from the data in the first activity? Well, first of all, it only gave us, it was missing some values, right? So it was missing n equals 0 and n equals 1. So it only gave us some of that. And then the growth factor was different. So when working with the table, how is calculating the missing value from the row above different from the row below? So remember when we were going above, so this is kind of like going backwards, if you will, we ended up dividing by the growth factor. Where when you're working in the row below, this is like going forward, and this is multiplying by the growth factor. So to go up the table, we divided by the growth factor. To go down the table, we multiplied by the growth factor. And then in the final question, why are both the initial height and the bounciness important? Well, because if you started a ball, so if we're looking at this, so if you started a ball, this ball at like 200, and then dropped it and it hits half its bounce, right? So let's say it keeps 50% of its bounce, then at this second one, it's going to be at 100, right? Where you could drop a different one from, let's say, 150, and it could keep, so it's going to be below it here, and then it could keep 90% of its bounce, and then it could be like up here, right? And then when you do the, like now those kinds of things could change information, or so it matters the height that you're dropping it, and it matters the position of it. And this is probably a bad example because we could do like where this one kept this much of it. So it's more, it's like more than 50%. But then here, when this one goes down, now maybe this one will be above it because its growth factor isn't quite as significant. So the fact that they started at the same, then the bounciness was the only thing that really mattered. It was the tennis ball is going to stay below it. Versus if one started higher than the other, then you'd really need to calculate each of the values to see if one was ever above or below the other. All right, for the lesson synthesis, was the data completely accurate? Why or why not? No, because we think there was something wrong in that third bounce of the other one, or of the first one. And you're always going to have human error when you're doing something. So sometimes stuff can be wrong. And we saw that one ball where it was mostly 53%. And then the third bounce was at 47. And that told us something felt weird. How do we decide if an exponential model is still appropriate? Okay, so as you keep going, is the growth factor staying the same? So is that growth factor continuing to represent what's happening? Why or why not? That will help you decide if the model is still appropriate. And then given the inconsistency, how do we find an appropriate factor to use for our model? So we just kind of ignored that third bounce since the fourth bounce was still about 53 to 54%. So we just kind of ignored it as if that was just a calculation error, kind of threw it out and kept on working with the rest of the data. Do the models we produce work well after 45 bounces or 78 bounces? And no, like this would be bad because the ball would just be stopped. like we said, stopped or rolling. Like you're not going to have a height of 0.0007 for your bounce. That's just the tennis ball is on the ground or the ball is on the ground. And really less than 1 centimeter, I mean, that's going to be on the ground. Can we rely on models to be appropriate if we bounce the ball on a different hard surface? This one was just talking concrete and told us that the 53% is what would make sense for a tennis ball there. We would have to compare it to the data for other surfaces if we wanted to do that. What level of accuracy should we consider? For example, is 0.5 and 0.54 more appropriate for the rebound factor? So which one is more appropriate? And they're basically the same. Okay, they're going to give you about the same results. 50% versus 54% when we're talking ball bouncing is probably fine. Obviously, 0.54 is more accurate, or more precise, I should say, but is it really truly accurate for the data? Depends on if the heights were right. So for this ball bouncing, probably doesn't really matter. For something more intricate and important, you'd probably want better data. So hopefully now you can use exponential functions to model situations that involve exponential growth or decay. And when given data, you can determine an appropriate model for the situation described in the data. To check your understanding for the lesson, make sure you do the lesson 11 practice problems. And if you need help with those, I have a video going over each problem in detail, so you can certainly find that to help you as well. You can also try this cool down and see how you're doing. If you're struggling on this, you're going to need to reach out to your teacher to get support from your teacher.